Hey there, and welcome to the lab. I'm so glad you're joining me for today's explainer because, well, we're going to be looking into some of the most fascinating and honestly, kind of magical invisible forces that are just hanging out all around us. You know that feeling when you see something and just think, wait, how on earth does that actually work? Well, that's literally what scientists do every single day. And today, you're the scientist. I'll be your host, your friendly neighborhood Red Dragon science guide, to be exact. Got my lab coat on, the beakers are bubbling away, and I am so ready for this. Why? Because we have an absolutely incredible scientific mystery to solve together today. We're going to be real detectives here, gathering facts, testing out materials, and even digging into a little bit of history. So let's just jump right in. Okay, take a really close look at this toy globe. Do you notice anything, well, weird about it? It's floating totally on its own. There are absolutely no strings attached to the top, zero hidden wires holding it up from the bottom. It's just hovering there in midair right above its base. I know it looks like pure magic, but I promise you it's 100% science. Our mission for this explainer is to collect clues and figure out exactly how it's pulling off that trick. So to crack this floating globe case, we kind of need to start with the basics, right? Clue number one, what exactly is a magnet? The box for that toy globe says a magnet is what makes it float, but what does that actually mean? Basically, a magnet is an object, usually made of iron or steel, that has this really cool superpower. But before we get into the power itself, let's talk about where they even came from. There's actually this wild story about how magnets were first discovered. Way back, there was this shepherd named Magnus. He's just out there minding his own business, tending to his sheep, and he's holding his walking stick, which happened to have a metal tip. Suddenly, boom! He makes this crazy discovery. The metal tip of his stick literally got stuck to this specific rock on the ground. He obviously didn't know it at the time, but he had stumbled upon a natural magnet. And today, we actually call that type of special rock a lodestone. Well, we've definitely come a long way since Magnus and his rock. Today, we figured out how to make magnets in all sorts of fun shapes and sizes for, different kinds of jobs. We've got your classic bar magnet, the long rod magnet, the circular ring magnet, the U-shaped horseshoe magnet, and even the tiny little button magnet. But hey, keep that ring magnet shape in the back of your mind, detectives. I have a feeling it might be super important for our globe mystery later on. All right, moving on to clue number two. What do magnets actually like? Or to sound a bit more scientific, what materials do they interact with? To figure this out, we're heading over to the laboratory sorting station. We're going to test a bunch of everyday materials to see which ones get pulled in by our magnets and which ones get completely, totally ignored. Okay, let's check out the results of our sorting game. Over on the left side, we've got our magnetic materials. These are things like iron nails and steel pins. Our magnet pulled them right over, no problem. But then, look at the right side, the non-magnetic materials. We've got a wooden ruler, some plastic, a ceramic bowl, glass, rubber tires, a cotton towel. The magnet couldn't have cared less about any of those. But check out the bottom right, because this is the surprising part. Aluminum foil and copper. A lot of people assume magnets just attract all metals, right? But our test proves that's definitely not the case. Magnets totally ignore aluminum and copper. So here's the big takeaway from that. A magnet only interacts with objects made of very specific magnetic materials. And as we saw in our sorting game, those magnetic superstars are basically iron and steel. If an object doesn't have iron or steel in it, our magnet is just going to walk right on past it. We are getting incredibly close to cracking this floating globe mystery. We know what a magnet is, we know what materials it likes. Now, for our third and final clue, we need to take a much closer look at the magnets themselves. Because, as it turns out, a magnet's pulling power isn't exactly the same all over its body. It actually has these secret power centers. Yeah, every single magnet, whether it's a bar, a horseshoe, or a ring, has two of these special power centers. We call them the North Pole and the South Pole. You see how those iron nails bunch up super tightly right at the ends of the magnet? That's because it's where that invisible pulling force is the absolute strongest. If you tried to stick an iron nail right in the dead center of a long bar magnet, it just wouldn't hold on nearly as tightly as it does at the very ends, the poles. And honestly, these poles are a huge deal outside the lab too. Did you know our entire planet Earth essentially acts like one giant magnet? It's true. It has its very own magnetic north and south poles. And because of that, ancient sea explorers figured out something pretty game-changing. If you take a magnet like, say, a lodestone carved into a spoon or a little magnetic needle, and you just let it hang freely so it can spin, it actually interacts with the Earth. That freely suspended magnet becomes a compass, and it'll always settle pointing directly north and south. Talk about a handy way to navigate the oceans, right? Okay, listen up, because we're about to cover the golden rules of magnets. This is where the real magic happens. So, what actually happens when two magnets bump into each other? Well, they follow some pretty strict rules. Rule number 1, unlike poles, so a north pole meeting a south pole, attract. They pull right toward each other. But rule number 2, like poles, meaning two norths getting shoved together, or two souths, they repel. They literally push each other away. I know, it's kind of hard to wrap your head around all this pushing and pulling since the force is totally invisible. But we can actually see this invisible force, which scientists call a magnetic field, by the way. If you take some fine iron powder and just sprinkle it around two magnets, the powder instantly snaps into this amazing pattern. You can actually see the lines of force either reaching out to grab the other magnet if the poles are different, or totally pushing hard against each other if the poles are the same. It's so cool. All right, my fellow scientists, time to flip open those clue notebooks. Let's review. We know magnets are made of iron or steel. We know they come in shapes like rings. We know they have north and south poles. And most importantly, we know that if you put two of the exact same poles together, they repel and push away. We've got all the pieces of the puzzle. It is finally time to solve the mystery of our floating toy globe. The secret is completely hidden inside the base of the toy and the bottom of the globe itself. Inside that base, yep, there's a ring magnet. And inside the bottom of the globe, you guessed it, another ring magnet. The engineers who designed this were super clever. They set up the magnets so that their like poles are facing each other. It might be north facing north or south facing south. But either way, because they're like poles, they repel. They create this powerful, invisible magnetic field that pushes the globe straight up into the air and just holds it there. Boom, case closed. Let's do a quick rundown of the amazing discoveries we made in today's explainer. Number 1, magnets absolutely love iron and steel. Number 2, their superhero strength is all bunched up at the ends, which we call the north and south poles. 3, opposites attract, so unlike poles pull together. And 4, the real secret behind our floating globe, like poles repel each other, which creates that incredible pushing force. So, now that you're in on the secret of how magnets can push things away and literally make objects defy gravity, I want you to put your inventor hats on. If we can use this invisible pushing force to float a little toy globe, what else could we use it for in the future? I mean, could we use giant magnets to build super fast hovering trains that don't even touch the tracks? What kind of crazy floating inventions can you dream up? Keep asking those big questions, keep exploring the world, and I'll catch you in the lab next time.